This is Physics 2120, Lecture 22, and today we're going to talk about displacement current and Maxwell's equations and begin talking about electromagnetic waves. So, when we first started talking about Ampere's law several chapters ago, that form that we used was valid only if any of the electric fields that were present were constant in time. And Maxwell modified the law to include time-varying electric fields. Maxwell added an additional term which includes a factor called displacement current. Now, displacement current is not a current in the conductor. Conduction current will be used to refer to current carried by a wire or another conductor. The displacement current is defined as epsilon naught times the time derivative of the electric flux. Remember, electric flux is the integral of E dot dA, and epsilon naught was the permittivity of free space. If we put those together, then we get something called the Ampere-Maxwell law that says the integral of B dot ds is equal to mu naught I plus I displacement, or mu naught I plus mu naught epsilon naught times the derivative of flux with respect to time. Now, why do we need this? Well, let's consider this loop that we're going to integrate the integral of B dot ds around. What do I mean by the surface that is bounded by that loop? Because I have two surfaces here I could consider. I can consider just this flat surface that goes across the front, or I could, like this was a bubble ring and I was blowing in it. Imagine a surface that's kind of blown back. In one case, I actually have current going through the surface, and in this case, I don't. But in this case, I have a capacitor and I have some flux going through that surface, and that flux going through it is the electric field times the area. And if Q is the charge on the plate, then the flux, which is EA, is just Q over epsilon naught. So, and that's the case, then the displacement current is epsilon d flux dt, which would just be dq dt. So the displacement current in this case is exactly the same as the conduction current going through the other surface. The displacement current on S2 is the source of the magnetic field on that surface boundary. So magnetic fields are produced both by conduction currents and time-varying electric fields. So I could either consider the current going through this surface to figure out my integral, or the time rate of change of the flux to this, which we just saw were exactly equal to each other. And this work by Maxwell really contributed to major advances in our understanding of electromagnetism. So in 1865, James Clerk Maxwell provided a mathematical theory that showed a relationship between all electric and magnetic phenomena. And Maxwell's equations were also used to predict the existence of electromagnetic waves that propagate through space. In his unified theory of electromagnetism, Maxwell showed that electromagnetic waves are a natural consequence of the fundamental laws expressed in these four equations. Gauss's law for electric fields, the integral of E dot dA is equal to Q over epsilon naught. Gauss's law in magnetism said the integral of B dot dA is equal to 0. Faraday's law, the integral of E dot ds is minus the time rate of change in magnetic flux. And the Ampere-Maxwell law, the integral of B dot ds is mu naught I enclosed plus mu naught epsilon naught times the time rate of change of the electric flux. Maxwell's equations are regarded as the basis for all electrical and magnetic phenomena. And his equations represent the laws of electricity and magnetism that we've already talked about, but they're going to have some additional important consequences when we put them all together. So let's review all four of these again real quickly. Gauss's law, electrical, says the total electric flux through any closed surface is equal to the net charge inside that surface divided by epsilon naught. And it relates an electric field to a charge distribution that creates it. Gauss's law in magnetism says the total magnetic flux through any closed surface is zero. This says that the number of field lines that enter a closed volume must equal the number that leave the volume. It implies that magnetic field lines cannot begin or end at any point. And we remember isolated magnetic monopoles have never been observed in nature. Faraday's law of induction describes the creation of an electric field due to a changing magnetic flux. And the law states that the EMF, which is the line integral of the electric field around any closed path, equals the rate of change of the magnetic flux through any surface bounded by that path. And one consequence is the current induced in a conducting loop placed in a time-varying magnetic field. And finally, the Ampere-Maxwell law, which is a generalization of Ampere's law. It describes the creation of magnetic fields by an electric field and electric currents. The line integral of the magnetic field around any closed path is the given sum. And once the electric and magnetic fields are known at some point in space, the force acting on a particle of charge q can be calculated from the force is QE plus QV cross B. This relationship is called the Lorentz force. And if I take Maxwell's four equations together with the Lorentz force law, that completely describes all classical electromagnetic interactions. Now, the two Gauss laws that we look at are symmetrical apart from the absence of the term for magnetic monopoles in Gauss's law for magnetism. And Faraday's law and the Ampere-Maxwell law are also symmetrical in that the line integrals of E and B around a closed path are related to a rate of change of fluxes. Maxwell's equations are fundamentally important to all of science. So, let's look at one of the consequences of these. Let's look at some place in empty space where there are no charges and no currents. Then the last two of Maxwell's equations can be solved to show that the speed at which electromagnetic waves travel is the speed of light. Now, this is a very important consequence, and the result led Maxwell to predict that light waves were actually electromagnetic waves. And Hertz came along and generated and detected these electromagnetic waves in a laboratory setting. And his most important discoveries were in the late 1800s. He showed other wave aspects of light. Hertz's experiment used an induction coil and was connected to a transmitter. The transmitter consisted of two spherical electrodes separated by a narrow gap. The coil provided short voltage surges to the electrodes, or sparks would go across. So as the air in the gap is ionized, it becomes a better conductor. The discharge between the electrodes exhibited an oscillatory behavior at very high frequencies. And from a circuit viewpoint, that was equivalent to an LC circuit. So sparks are induced across the gap of the receiving electrodes when the frequency of the receiver was adjusted to match that of the transmitter. And in a series of other experiments, Hertz showed that the radiation generated by this equipment exhibited wave properties: interference, diffraction, reflection, refraction, and polarization. We're going to get to all of those in the next few chapters. And he also measured the speed of that radiation. So, we're going to assume that the vectors for the electric and magnetic fields in an electromagnetic wave have specific time-space behavior that's consistent with Maxwell's equations. So we're going to assume an electromagnetic wave that travels in the x direction with the E and B directions of the field as shown. The x direction then is the direction of propagation. E then we're going to assume is in the y direction and B in the z direction. Waves in which the electric and magnetic fields are restricted to being parallel to a pair of perpendicular axes are said to be linearly polarized waves. We also assume that at any point in space, the magnitudes of E and B of the fields depend only on their position and on what time it is. So some other definitions we need to talk about are a ray. A ray is a line along which a wave travels. All the rays for the type of linearly polarized waves that have been discussed are parallel. And a collection of all those waves is called a plane wave. The surface connecting points of equal phase of all the waves is called a wavefront, and in this case would be a geometric plane. The solutions of Maxwell's third and fourth equations are wave-like, with both E and B satisfying the classical wave equation, where the speed of those electromagnetic waves travel at 1 over the square root of mu naught epsilon naught. And this comes from solutions of Maxwell's equations, which we will look at. Now, this was an extremely interesting discovery, because remember, epsilon naught is the constant that relates the force between two charged particles. It's Q1, Q2 over their distance squared, and 1 over 4 pi epsilon naught is the proportionality constant. So it has to do with a force between charges. And mu naught had to do with the force between current-carrying wires. And why these fundamental quantities have anything to do with the speed of light was a puzzle back in the late 1800s. We were just trying to figure out what exactly light was. Was it a particle? Was it a wave? And Maxwell kind of brought this all together. The components of the electric and magnetic fields of plane electromagnetic waves are perpendicular to each other and perpendicular to the direction of propagation. That can be summarized by saying that electromagnetic waves are transverse waves. The magnitudes of the electric and magnetic fields in empty space are related by the expression C is equal to E over B. And this also comes from the solution of the partial differential equations obtained from Maxwell's equations. Electromagnetic waves also obey the superposition principle. So let's consider a problem. A sinusoidal electromagnetic wave, frequency 40 megahertz, travels in free space in the x direction. Determine the wavelength and the period of the wave. Also, at some point in time, the electric field has a maximum value of 750 newtons per coulomb. It's along the y-axis. Find the magnitude and direction of the magnetic field at that point. So first, we know that the speed of a wave is equal to its wavelength times its frequency. So the wavelength is the speed over the frequency, which should be the speed of light divided by 40 megahertz, and we get 7.5 meters. The period of this wave is 1 over the frequency. Now it's 2.5 times 10 to the minus 8 seconds. That's the time it takes for the electric field to go from a maximum in the y direction to come back to that same maximum. We also know that the speed of light is the maximum electric field over the maximum magnetic field, so Bmax is E over C. And then we get that the maximum magnetic field is 2.5 times 10 to the minus 6 Tesla. Now, the derivation of the speed of light from Maxwell's equations is very important, and so I want to go through it once so that you can see it. I'm just telling you that you may want to know how to derive the speed of light using Maxwell's equations, as I'm about to do now. So, we'll start with the integral of E dot ds is equal to minus d flux dt. So, first, let's look at a small region of space here. I have an electric field here, and I'm looking at an infinitesimally small plane here. So the electric field over here is this electric field plus whatever change there is in the x direction. And we can Taylor expand this. The electric field at x plus dx is essentially the electric field at x plus however it's changing, the derivative tells me how it's changing, times the distance dx that I go across. So the electric field at this point is the electric field at this point plus the derivative of the electric field with respect to x dx. Now this fancy differential symbol here just means partial derivative. It means in the expression for electric field, treat any other variable as constant except for x. So if I take this value and I put it in the integral of E dot ds, well, the electric field is in the y direction here, so it's going to be the electric field at this point times the length of this box minus electric field at this point times the length of the box. And when I put that in, all I get is the derivative of E with respect to x dx times the length of the box. The flux through the loop is given by the length times the width, so that's the area, L dx, and B is the magnetic field through it. So I take the derivative, L and dx are constant in time, so it's just dB dt. So d flux dt is L dx dB dt. Putting those together, I end up with the partial of E with respect to x dx times L is minus L dx partial of B with respect to t, or the L's and the dx goes away. The partial of E with respect to x is equal to minus the partial of B with respect to t. We're going to save this equation. We'll come back to it in a minute. Let's repeat this with our equation for magnetic field. In the absence of any currents, the Ampere-Maxwell law becomes the integral of B dot ds is minus mu naught epsilon naught d flux dt. And we're going to expand B in the same way we did before. We can say that B at this point over here is B at this point plus however B changes across this field times the distance across that. So that's B times dB dx times dx. We can take this then and plug it into our integral, and the integral of B dot ds is B times L minus whatever the value of B is here times L. And when we plug this in here, we get this value here, minus dB dx times L. Now we need to know what the flux through it, d flux dt, is L dx dE dt. And putting those all together, in this case, gives me the partial of B with respect to x is minus mu naught epsilon naught times the partial of E with respect to t. We then have these two equations. The partial of E with respect to x is minus dB dt, and the partial of B with respect to x is minus mu naught epsilon naught dE dt. Let's take the partial derivative of the first equation with respect to x, and we'll take the partial derivative of the second equation with respect to t. So in that case, this side becomes a second derivative of v with respect to x, and this is the partial of b with respect to x and t. But this is the partial of b with respect to x and t, that's minus mu naught epsilon naught, partial of e with respect to t squared, and we can equate these two and give us an equation that only deals with electric fields. It says the second derivative of the electric field with respect to x squared is mu naught epsilon naught, the second derivative of the electric field with respect to t squared. So from Maxwell's equations, when we apply them to empty space, we get this equation, and I could have also solved it the other way for just the magnetic field and got an identically looking equation. And if we remember back for the general wave equation, it says the derivative of the function with respect to x squared is 1 over the velocity times the derivative of a function with respect to t squared. And we compare the general wave equation with either one of these, we see that the velocity of this wave is just exactly the speed of light. If we put in mu naught and epsilon naught, it gives us c is 2.99792 times 10 to the 8th meters per second, which is precisely the speed that we measure of light. The simplest solution to those partial differential equations are just a sinusoidal wave. So the electric field is some maximum value times cosine of kx minus omega t, where k is the angular wave number, 2 pi over the wavelength, and the angular frequency omega is 2 pi times the frequency. The speed of the electromagnetic wave is omega over k, which we said is 2 pi f over 2 pi over lambda, which is lambda f, which is just the speed of light. If we take the partial derivations, it also gives that E max over B max is omega over k, which is E over B, which is just the speed of light. So then we can get a representation of what an electromagnetic wave looks like. A sinusoidal, linearly polarized plane wave moving in the x direction, where the electric field varies in the y direction sinusoidally at the same time as B varies in the z direction sinusoidally, and they are in phase with each other. Looking at an electromagnetic wave coming at me, then, the electric field will grow and the magnetic field will grow, and they'll get to some maximum value. Then they'll shrink back down, and then they'll go to a maximum value in the other direction and shrink back down. Now, one of the things about electromagnetic waves is they carry energy. In fact, this is the main way we get energy transfer in the universe. So as they propagate through space, they can transfer that energy to any object in their path. The rate of flow of energy in an electromagnetic wave is described by something called the Poynting vector, S. The Poynting vector is defined as 1 over mu naught times the electric field crossed with the magnetic field. Its direction, then, is the direction of propagation. And it's time dependent. Its magnitude varies in time, and its magnitude reaches the maximum the same time the electric fields and the magnetic fields reach a maximum. The magnitude of S represents the rate at which energy flows through a unit surface area perpendicular to the direction of wave propagation, or it's the power per unit area. So the SI units of the Poynting vector are watts per square meter. The intensity of a wave, I, is the time average of S, the Poynting vector, over one or more cycles. When the average is taken, the time average of cosine squared of any function is always 1/2. And so the intensity, which is the average Poynting vector, is E max B max over 2 mu naught. Or, playing with it, I could say it's E max squared over 2 mu naught C, or C B max squared over 2 mu naught. The energy density, lowercase u, is the energy per unit volume. Remember that the energy density of an electric field is 1/2 epsilon naught E squared, or for a magnetic field it's 1 over 2 mu naught B squared. And since B is equal to E over C, and C is equal to 1 over the square root of mu naught epsilon naught, the energy stored in the magnetic field is the same as the energy stored in the electric field, and we could look at either one. So the instantaneous energy density associated with the magnetic field of an EM wave equals the instantaneous energy density associated with the electric field. So in a given volume, the energy is shared equally by the electric and magnetic fields. The total instantaneous energy density is then the sum of the two energy densities. And since they're the same, it's either going to be epsilon naught E squared or B squared over mu naught. When this is averaged over one or more cycles, the total then becomes the average of each of these, which is going to be 1/2 epsilon naught E max squared, or B max squared over 2 mu naught. And in terms of intensity, the intensity is equal to the average Poynting vector, which is C times the average energy. The intensity of an electromagnetic wave equals the average energy density multiplied by the speed of light. So let's look at an example problem. Let's estimate the maximum magnitudes of electric and magnetic fields from a light from a desk lamp on a piece of paper underneath it. So let's assume we have a 60 watt light bulb. We're going to treat the bulb as a point source of electromagnetic radiation that's 5% efficient at transforming energy coming in by electrical transmission to energy leaving by visible light. There's other forms of energy that are coming off. We're just going to look at the visible light that's coming off. So, the intensity of a point source, we learned back when we did sound waves, was the average power over 4 pi r squared, which in this case is also Emax squared over 2 mu naught c. So the maximum electric field solving that equation is going to be mu naught c times the power average over 2 pi r squared. So we're going to assume our lamp is maybe 30 centimeters above the piece of paper. It's a 60 watt light bulb, but only 5% is actually coming out in the form of visible light. So that plugging all that in, I get a maximum electric field of 45 volts per meter. We can then use the relationship between E, B, and C to get the maximum magnetic field, which would be 1.5 times 10 to the minus 7 Tesla. So let's review what we talked about today. We started with displacement current and how its displacement current is related to changing electric fields. And Maxwell used that to modify Ampere's law to get the Ampere-Maxwell law, and he came up with all 4 of these together, which we call Maxwell's equations, and they, together with the Lorentz force, are the basis for all electromagnetic theory. We went through electromagnetic waves and what they are, and how Maxwell's equations lead to electromagnetic waves at the speed of light. And we looked at how to derive the speed of a wave using Maxwell's equations. And lastly, we talked about intensity in Poynting vectors.